Okay, so geometrical optics. Okay. Or this is also called ray optics. So this is a section of optics where we study two important properties of light, okay, namely reflection and refraction. So
So how many topics are left in the waves chapter? So we can leave that many pages then.
you're currently doing sound, no? Right?
Yes, sir.
In Red House, right? You're doing sound.
Yes, sir.
Yeah. So in sound, we have reached where we have just about come to general equation of wave and intensity, right?
So we haven't started Shome.
We had done about nodes.
Last lecture, what we have done, standing waves in a
Standing
string.
waves, nodes, antennas.
Nodes and okay. So do one thing, na, just keep sound as a separate topic, na, so you can continue with geometrical optics now.
Okay, sir.
Understood? Na? You can just do that way in your notes. Okay. Okay. So reflection and refraction of light. Okay. So yeah, Shikhar, Blue House, you can leave about 6-7 pages for completion of wave optics. Okay. Okay. Right. So let's come back to the topic. So reflection and refraction of light. So in this section, we treat reflection and refraction like, experimental laws without worrying about what nature of light, whether it is a wave nature of light or the so-called particle nature. In fact, we will study later in wave optics that it is the wave nature of light only which creates reflection and refraction. Okay. So the laws of reflection and refraction can be justified by the wave nature of light itself. But in this section here, we will not worry about that thing. We will treat it like they are known laws experimentally or empirically, and we will study the properties of light based on these two laws, which is reflection and refraction. So we begin this section by understanding the laws of reflection and refraction, treating them like experimental laws. Okay. In fact, they were experimental laws. Okay. They were discovered long before electromagnetic waves were understood and light was understood as a wave. So it's justified in that sense. Okay. If we go historically in physics. So anyhow, so let's understand the laws of reflection and refraction. So we'll start with laws of reflection. So sure you have heard of these in class 9, 10th before also. The law of reflection, I mean, there are two laws of reflection. The first one states that if we have a ray of light incident on some reflecting surface, then after reflection, okay, it deviates in such a way, or you can think of it like bounces back in such a way that the angle of incidence is equal to the angle of reflection. So what is the angle of incidence and what's the angle of reflection? Let's understand that. So at the point of incidence, if we draw an imaginary normal to the reflecting surface, okay, the angle made by the incident ray with respect to that normal is called the angle of incidence, and we can denote it with the symbol I, let's say. Similarly, the angle of reflection is the angle made by the reflected ray with respect to the normal. Okay. So let's say this point P is the point of incidence. So the first law of reflection is that angle of incidence is equal to angle of reflection. So first of all, what are these? Let's understand. So I is the angle of incidence which is the angle made by an incident ray, okay, with respect to the normal to a reflecting surface at its point of incidence. And similarly, R is the angle of reflection. So again, that is the angle made by the reflected ray with respect to the same normal. So in this diagram, you can understand that this is the incident ray and this is the reflected ray. And this is what we generally call a plane mirror or a plane reflecting surface. And the second law is that the incident ray, the imaginary normal that we have drawn over there, and the reflected ray, these three are coplanar. So we'll understand this now better in context of how you learned vectors. If you define a unit vector along the incident ray, a unit vector along the reflected ray, and a unit vector normal to the surface at that point of impact or at the point of incidence, then the three unit vectors have to be coplanar. They have to lie in a common plane. So you can visualize this three-dimensionally like this. That if this is, let's say, a reflecting surface, and we have an incident ray like this over here. So these have to lie in a common plane. Okay. So whatever is the plane in which these two are lying, this will lie in the same plane with it. So this. Okay, so at this stage we can treat this like an experimental law. Okay. Though it can, I can show you later when we are discussing about wave optics that this can be justified from the wave nature of light. Okay. Now let's see some more instances of this kind of situation. So when we say angle of incidence is equal to angle of reflection, it doesn't apply only to a plane reflecting surface. We can also have a situation where we have, for example, a spherical reflecting surface. So you can have a situation like this, which is an example of a convex reflecting surface. Or we can have an example like this. Concave mirror. So here also, if we have incidence like this, then what we do is at the point of incidence P, we draw normal by joining it with the center of curvature. So this line here becomes our normal. The reflection occurs in such a way that angle of incidence is equal to angle of reflection. Okay, so here this C is the center of curvature. Okay. And finally, if we have, like, let's say some random shape of mirror, random shape of a reflecting surface, and we have some incidence like this, then what we have to do in such a situation geometrically to understand where the reflected ray will lie is that at the point of incidence we have to first draw a tangent to the reflecting surface. So this is the tangent at the point of incidence. Okay, and then we can draw the normal by just drawing a line perpendicular to the tangent. So this becomes the normal. So then finally the reflected ray will be something like this over here. Okay. So this is the literal application, or you can say the literal interpretation of the laws of reflection for various types of reflecting surfaces. Okay, so now based on this, we look at our first direct application of laws of reflection. Reflection by a plane mirror. So if there is any point object, who in this case is a point object, and there is some observer present anywhere, then to the observer it will look like there is a what we call a virtual image of the point object behind the mirror at the same distance. Now let's observe why that happens. It happens because any ray which is incident like this is reflected back like this. Draw a series of rays, for example. So rays which are incident like this, they suffer reflection in such a way that angle of incidence is equal to angle of reflection. So if you produce such reflected rays back, they show us that they appear to be coming from a virtual point behind the mirror, which is at the same distance as this one is in front. Okay. So if you see here, this angle, let's say theta, is equal to this angle theta. So here, this angle theta is equal to this angle theta. Okay. So similarly here, if this angle is some phi, this angle will also be phi. So all these triangles, they are congruent. Okay. So therefore, if this distance is x, then this is x behind. Okay. So a point object, the rays of light incident on the mirror from the point object reflect such that they appear to be coming from a point behind. Okay. So hence a point object produces a virtual point image which is at the same perpendicular distance behind the mirror as the object is in front. emanated, appear to be emanated. So these rays, the reflected rays, you can see they appear to be emanating from this virtual point I behind the mirror. Okay, so once we understand this situation, we can see that reflection by a plane mirror for any what we call extended object. This was a point object. Now, suppose we have any extended object, the image becomes an extended image. Suppose we have an extended object like this, AB. Then the reflection of light from every point in this object happens in such a way that, for example, so E's image appears to be here, let's say A prime. But like that, you take any point on the object, its image due to reflection will appear to be like this now at this point. So every point has a virtual image of it behind. So this becomes the virtual image for the object AB, such that this distance is equal to this distance. This height is equal to this height. So an extended object will produce an image which is of the same size We're discussing in context of plane mirror only. Okay. So okay, so let's understand what lateral inversion means. If this is the object, then the image will appear to be like this. Right becomes left and left becomes right. Okay. If this is the object, the image will appear to be like this. Okay, so this is very simple and obvious part of geometrical optics. Nothing very difficult here. So let's look at a typical application example type of question.
So can you show the above diagram for a second?
Yes.
Yes, sir.
Just a moment. Okay. So this is a plane mirror. Which I'm taking, suppose, in the YZ plane. Because I'm taking this as my x-axis and this as my y-axis. Now what is happening here is that a point object is moving with a velocity like this. So a point object so we want to find the velocity of its image and the velocity of the image relative to itself. Okay, I'll just go back to the previous section once. We'll come back to this question. Okay, let's come to the question now. So to deal with this question now, what you have to keep in mind is that at any point of time, the image of that object O will be behind the mirror at the same distance as the object is in front. Okay, so keeping that property in mind, try to visualize how the image will be moving as the object moves like this. You can also break the velocity of the object into two components, parallel to the mirror and perpendicular to the mirror. And then try and use superposition, that if the object was moving with only one of the components, then how the image would be moving, and then superimpose. Yes, very good. Aman, Harsh, and Snikita, your answer is correct. So what we can understand here is that for a plane mirror, if we have an object moving directly towards the mirror normally, with a velocity v like this, then if this distance is x1, v1 is minus dx1 by dt. At any instant, the image will be behind the mirror such that x2 is equal to x1. So dx2 by dt should be equal to dx1 by dt. So that means dx2 by dt should also be minus of v1. So this image should therefore have a velocity which is like this. Okay. And the velocity of the image should be equal to velocity of the object, but opposite in direction. Okay. Whereas same thing if you visualize an object moving parallel to a mirror, then because the perpendicular distance should not be changing with respect to time, so the image should be moving also parallel to the mirror in such a way that x1 remains equal to x2 at any instant. So this is at some time t, then at some time t plus delta t. Now the image should be at the same perpendicular distance behind. So this will tell you that if it's a parallel velocity, then v1 is equal to v2. If it is a normal velocity, then it's opposite in direction. So putting together these two things, you can see that in the above case, what will happen is that in this kind of a situation,
Sir, V2 will be equals to minus of V1 now in first case.
yeah, I mean, if you write with sign convention, it will be, so
In
already showing the
magnitude, they
direction.
will be equal.
Yes, it will be equal and opposite in the case of the normal velocity. So that is shown in the direction, in the vector direction. You see, v2 is opposite of v1, whereas in the parallel case, it is the same direction. So here the velocity of the image will become like this, such that the component of the velocity of the image, which is normal, is equal and opposite. Okay. So if this was 6 I cap, this is minus 6 I cap as a vector. And if this was 8j cap, then this is plus 8j cap. So the velocity of the image, the absolute velocity in the ground frame, will become minus 6 I cap plus 8j cap. So you can see that the velocity of the image relative to the object is going to be minus 12 I cap. So to the object, it will look like the image is coming directly towards it normally in the perpendicular negative x direction at double the speed. Okay, people. So nothing really much more about reflection at plane surface. Okay. You can get some questions related to relative motion of this type, but nothing more complicated than that. Usually plane mirrors will be incorporated at JEE level questions in a system which has more number of things. So reflection by the plane mirror is one of the things. Like there might be a lens in front of the plane mirror and an object on the other side of the lens. So you have to just make use of this property of the mirror. So we'll come back to that. Okay. In those type of systems, we'll come back to that, but this is all the property. Next, we move on to reflection by spherical mirrors. Okay. So this is again something that I think you are familiar with from class 9, 10, the UV formula. But here we will do the derivation of those formulae and understand the sign convention in more detail. So that again, when it comes to more complex questions where there is combination of lenses with mirrors, etc., you are easily able to solve. So let's start with concave mirrors. So concave mirrors are basically spherical reflecting surfaces such that what we have done is we have silvered the glass. So let's say we have a glass sphere, okay, and then we split it. So we are left with only a section of the glass sphere. Okay, so this is a part of a spherical shell, okay, spherical glass shell. And now what we do is we silver it from outside. So the inner part is reflecting. So this is where the silvered, so it's silvered on the convex side. So the concave side becomes a reflecting surface. So this is a concave reflecting surface. So this was, let's say, the center of curvature. This is on R. So R is the so-called radius of curvature. Okay. So as we've discussed earlier, that if you have any incident ray at any point, let's say like this, and after reflection, it will go off such that angle of incidence is equal to angle of reflection. So here this angle will become equal to this angle at whatever point of incidence. So this is the general principle we'll apply for concave mirrors. And using this, you'll see how to develop a formula for the position of the image for a given object in front. And from that, we will understand the whole concept of focal length and things like that. Okay, so next thing, let's understand.
So just for 1 second, can you show them again?
Yes.
Yes, sir. Thank
Okay. Okay, so once again, let's consider this is our center of curvature. So this is a concave mirror. Okay, now if we have kept a point object, let's say over here, so then the line joining the center of curvature with the point object, that is called the principal axis. This line. And wherever the principal axis meets the mirror, that point is called the pole. So what will happen is that a ray of light incident from the object along OP, that is along the principal axis, will just reverse its path because its angle of incidence is 0. Okay. So understand here that consider a ray of light incident like this along the principal axis. It has a 180-degree deviation. It just reflects back. It retraces its path. Now, if you consider another ray of light, which is incident at any other point, like this, let's say. So consider a ray of light which is incident at the point E, like this over here. What will happen to this after reflection? So for that, we have to understand where the normal lies. So at its point of incidence, this is going to be the normal. Okay. So the angle of incidence for this one is going to be this angle here. This is the angle of incidence. Okay. So as you can understand from the laws of reflection, this will after reflection tend to go like this. And it will meet up with the principal axis. So it will intersect the principal axis at some point, let's say. Now, if we are able to show that all such reflecting rays meet at the same point, all such reflected rays come back to the same point. If we are able to show that, then we can say that, okay, this point will become the point image of O. But we still have to prove that all reflected rays, it's not just this particular one that meets the principal axis, but all reflected rays are going to intersect at a common point, then that will become the image of that point. And as you can see, in this case, it is a real image because they're actually intersecting at this point. So to observe that image, actually, we will have to place a screen at that point I, or a photographic plate, which will receive that image. We'll not be able to see this image with the naked eye like we see for a virtual image. It's not behind. So imagine O is a small LED bulb or a candle tip or something. O is a point object. Okay. So now I in this case is its image. So basically, to show that it's the image, we will show that all reflected rays converge to the point I. Then only we can show that. Okay. And then from that, given the distance OP, we want to find the distance IP, how much this will be. So that is the problem at hand only. Okay. So what we now do is that, first of all, we'll apply the law of reflection, that angle of incidence is equal to angle of reflection over there. And then we designate some more angles. We take this angle as alpha. We take this angle here as beta. And we take this angle as gamma. So now we can see that considering triangle OCA, okay, look at this triangle OCA. So you can see I and alpha are interior angles and beta is the exterior opposite angle. So beta will be equal to the sum of alpha plus I. Exterior angle is equal to the sum of interior opposite angles. Okay. And similarly, for triangle, we take CIA, because we like the name. Okay. Gamma will become the sum of beta plus R. Okay, so make sure you understand these two equations that we have written. They are both based on the same principle, that exterior angle for a triangle is equal to the sum of the interior opposite angles. But here the two triangles that we have considered to express these laws are triangles OCA and triangles CIA. So right now we are just considering this based on the geometry of a particular incident ray, which is incident at the point A. But what we will show is that the geometry of this is such that the position of the point I, where the reflected ray meets the principal axis, is going to be the same for all such triangles or all such incident rays, irrespective of which point they are incident at. That means irrespective of alpha and irrespective of the angle of incidence and reflection. So we'll understand in a moment how that works. So let's say this is our equation 1. And this is our equation 2. So from 1 and 2, we have I is equal to, and from 2, okay, so I is equal to R implies that, so we have okay. Now comes the more critical part. Okay. So for this equation now, if we consider alpha to be a small angle, that is less than about 5 degrees. Small angle definition from trigonometry type only, that type thing. Okay. Then automatically you can see from the diagram that beta and gamma also become small angles. Okay. So in that case, we are considering in our diagram more something like this. We are considering rays which are very close to the principal axis actually. These type of rays we are considering. So then the incident rays, they are called paraxial. Okay. Paraxial means nearly parallel to the principal axis. So when we do that, then we can consider alpha, coming back from that diagram over there. Okay, we can consider alpha as almost equal to the arc length AP divided by OP. Beta is of course exactly equal to the arc length AP divided by CP, because C is the center of curvature of that arc. And in the same instance, gamma again gets approximated as arc length AP divided by IP. So these approximations that we have written, this one and this one, they are subject to this condition that they are paraxial rays. Subject to this condition.
So it is only for alpha, gamma, or all of them?
Okay, so now you can see that if we incorporate these in the formula that we got on the left hand side, here this formula. So this thing that alpha plus gamma is equal to 2 beta. This now implies that arc length AP upon the object distance OP plus the same arc length AP divided by the image distance IP becomes 2 times the arc length AP divided by the distance of the center of curvature CP. So we get a relationship between object distance, image distance, and radius of curvature. Okay. And what this shows you is that as long as alpha is a small angle, that means we are considering paraxial rays, then this relationship is independent of the value of alpha. So whether alpha is 2.5 degrees or 1 degree or 0.5 degrees or whatever, all paraxial rays after reflection are going to converge to the same point I. Okay, and because paraxial rays in any case form the majority of the incident rays over here, so that means we are going to get an actual image. I mean, this is the theoretical proof that we'll get an actual image at the point I. Of course, we can conduct an experiment and from that verify it. And not only this is a proof that we will get an image at that point I, but it gives us, more importantly, the formula for the relationship between object distance and image distance. So what this shows us is that this implies that all paraxial rays after reflection converge to the same point I, such that further implies that I becomes the real image of the point object. Oh. Okay. So we will convert this into a UV formula also, but for that we will incorporate the Cartesian sign convention in this. So right now just think of it like a relationship between 3 distances. The distance OP, the distance IP, and the distance CP. Yes, exactly. We can get the UV formula, Jagannath, but the thing is now we have to incorporate the sign convention. Okay. So now next thing we see, because otherwise we'll get a different formula for different situation. Okay. So Cartesian sign convention. So in this case, we are applying Cartesian sign convention to a concave mirror, but it's actually irrespective of that. Concave or convex mirror or lens, whichever be the case, we'll apply the same Cartesian sign convention. Okay. So if this is the pole, then any position to the left of the pole is written as a negative quantity, and any position to the right of the pole is written like a positive quantity. So for example, if we have a point P1 over here where this distance is x1, and a point P2 over here where this distance is x2 with respect to the pole. So in Cartesian sign convention, the position of the point P1 will be written as minus x1, and the position of any point P2 on this side will be written as plus x2, like this. So coming back to the above diagram with Cartesian sign convention, so incorporating the Cartesian sign convention, so in Cartesian sign convention, we always write u as position of object. Okay. We write v as the position of image, and we write r as position of center of curvature. So all these three are with sign, with the proper algebraic sign. So in a situation like the above case, where with respect to the pole, the center of curvature is here, the image was formed here, the object was here because of this sort of reflection. So again, in the diagram for ease, I'm showing rays which are not really paraxial. These angles are pretty large, but you have to imagine for paraxial rays. So this formula, in this u becomes minus of OP, P becomes minus of IP, and the position of the center of curvature becomes minus of CP. So 1 upon OP plus 1 upon IP is equal to 2 upon CP. This implies that 1 upon minus U plus 1 upon minus V is equal to, in this case, 2 upon minus R. So we have the formula 1 by V plus 1 by U is equal to 2 by R. So I'll just minimize this a little. You can understand the final few steps. Okay. It's quite critical, so make sure you understand all the aspects of this derivation first. So once this derivation is clear, all other derivations will follow in the same manner, so there won't be any difficulty. Okay, so far we will just treat this as if this is the formula for the concave mirror. Okay, we'll later show that with sine convention we get the same formula for convex mirror also, but let's so far just assume that this is the formula that we have for concave mirror. Okay, where when we are actually doing the application of this in a numerical problem, we must substitute all the quantities with proper sign. Okay. So this is the mirror formula. Right now we'll just say it is for convex mirror. Sorry, concave mirrors, my mistake. Taking the example of a concave mirror. It will actually be the same for the convex mirrors also when we come to that. Okay. And U, V, R are with algebraic sign in this formula. Okay. So let's look at an example. We have a concave mirror of radius of curvature, let's say 60 centimeters. Okay. And a point object is placed at a distance of say 180 centimeters, 45 centimeters, and 15 centimeters from its pole. So find the position and nature. By nature we mean whether it is real or virtual of the image produced in each case. So let's work this out on the board. I'll give you more questions to do yourself. Okay. But let's understand not only the application of the formula, but the interpretation of the result in each of the case. Okay. So I'll write down the question first. Okay, now one way to interpret the above question is that we place the mirror like this. We place the mirror like this. Left of the pole. So we are having to keep the object also to the left of the pole. So now the center of curvature is, let's say, over here. The pole is here. So anything on this side is negative, anything on this side is positive. So in the first case, when we take the distance OP as, what was it, 180 centimeters. Okay, CP is of course 60 centimeters. So we're keeping the object here. So using the UV formula, we will put U as how much? 1 minus 180. And we'll put radius of curvature, I mean the position of the center of curvature R as minus of 60 centimeters. And we'll use the formula 1 by V plus 1 by U is equal to 2 by R. So by using the formula, let's see what we get for the position of the image. So you get 1 by V as -1/30 plus 1/180. So it will give us a negative quantity, as you can see. Okay, give us -5/180. Is that correct? Yeah. Okay, so what is the interpretation of this now? So the interpretation is that, see, V is negative. That means the image will be where now? And it's 36 now to the left, and this is 60. So the image will be somewhere here, let's say. Okay. So this corresponds to the ray diagram of the type we had discussed earlier. It corresponds to some ray diagram, which is a bit like this. Just imagine these rays to be paraxial. They don't look paraxial in my diagram here for obvious reasons, but something like this is happening. So you can see that it is a real image that is in front of the mirror. At a distance of 36 centimeters from the pole. Now, the point that I also want to show you is that there is no hard and fast rule that we always have to place the mirror like this. We could have also placed the mirror like this, facing the other side. And if we do that, it's not like we have to suddenly change our sign convention and make the right hand side negative and the left hand side positive. You can stick to the same sign convention that this side is positive and this side is negative. So here the center of curvature is over here. Okay, and the object is placed somewhere over here. So in this case, our U will be taken as plus of 180. Our R will be taken as plus of 60. And using this formula, we will get V as plus 36. Now this will have the same interpretation. Okay, because now the space in front of the mirror is our positive side. Okay, so this is the advantage of the Cartesian sign convention. And you don't have to switch things. You don't have to switch the formula also. We'll see later when we switch the side in which the mirror is placed, or when you switch a mirror from concave to convex or something, you don't have to alter the formula. No, you can always switch also. It's fine. You can switch the sign convention, make this side negative, that side positive. Then also you'll get the correct answer, because basically you are just multiplying both sides of the equation with a minus sign. No? You're multiplying the whole equation with a minus sign. So it doesn't make a difference. You're understanding the point? If I say x is equal to y, minus x is equal to minus y is also correct. Okay. But the thing is, we don't need to do that. Okay, we can just use a Cartesian sign convention. Means it's like a Cartesian coordinate frame based kind of system. So it is independent of all that. Okay, so now just try out the second and third part. Okay. Yes, correct, Harsh. Very good. Just tell me the distances also. Okay. The positions in centimeters also. So actually, when we give the answer for this, we need not give with algebraic sign. We can just say that it's a real image in front of the mirror. Whereas had it been a virtual image, it would have been behind the mirror. Now, whether that behind and in front is positive or negative, that is up to our sign convention. But the physical reality of it is that it's either a real image which is formed in front of the mirror by actual convergence of reflected rays, or it's a virtual image that appears to be coming from that point behind the mirror because the rays are diverging. The reflected rays in that case would be diverging. Okay. Okay, so let's verify the answers in each of the cases. Okay, so we had taken 180 as the first one. Okay, then next case, we just visually understand it first. So we had taken the object in the next case somewhere here, because we had taken the object at, what was it, 90 centimeters, right? 45 centimeters, sorry. 45 and 15. So second part. Okay. So here we'll take U as minus 45, R as minus 60. So 1 by V plus is equal to 2 by R. So this now means okay. So this is a real image, 90 centimeters in front. And now the C case is the one which is quite interesting. Now in this, what we'll see is that the object is placed somewhere like this, because it's less than half the radius of curvature. So we will put U as minus 15, R as minus 60. So when we get so plus 30 means it becomes a virtual image. "30 centimeters behind the mirror." So let's understand why this happens. Okay. Okay, so such an incident ray after reflection will become divergent. Doesn't converge, but it becomes divergent such that it appears to be coming from behind the mirror. Hence the virtual image. So this is the ray diagram corresponding to the situation. No, and we don't consider size for point objects. We will come to extended objects and magnifications next. Okay. Okay, so this is incorporation of this. Okay, now let's look at convex mirrors. Now you'll see that the relationship between the distances, if we write, of the image object and the center of curvature, that relationship is a little different. But when we incorporate the sign convention, we'll get the same relationship as before. Okay. So that is where the advantage of Cartesian sign convention comes in. We don't have to switch the formulae for the different types of mirrors. So convex mirror means that we have silvered it from the inside, and the outer convex surface is the reflecting surface. Once again, this point is our pole. Let's say this is our center of curvature. Now let's consider a point object somewhere in front over here like this. Then any incident ray over here like this. We consider the normal at the point of incidence. That will be this line. So let's again take the point of incidence as A. Okay. So now you can see this angle becomes the angle of incidence. Okay. So after reflection, it has to deviate in such a way that so when you produce the reflected rays back, they appear to be coming from a virtual point I like this over here. So to find the relationship between the three distances, object distance, image distance, and center of curvature's position, we will again incorporate the same kind of method. We will designate this angle as alpha, this angle as beta, and this angle as gamma. So we have I is equal to R. That's our law of reflection. Yep. Now we can start incorporating this like this, that for triangle OCA, we have I is equal to alpha plus beta. And in triangle CIA, if gamma is equal to R plus beta. Because this angle you can see, it's R. Okay. So we have this equation. So now again for paraxial rays, alpha being a small angle,
Sir, what is that cosine on PA?
what is that? Arc length, beta. Same as in the previous derivation.
Okay.
So we have the relation. You can see in terms of distances, it's a different relation. But when we incorporate Cartesian sign convention, So it's the same formula. Okay, so now from this, let us interpret focal position or focal point f and focal length for a mirror. So focal point is defined as the position of the image for what we call a distant object, that is very far away object. That is a simple definition. So when you look at the formula, 1 by v plus 1 by u is equal to 2 by r. So here when we put u tending to infinity, the position of the image becomes the focal position. Of course, whatever we are doing is with Cartesian sign. So in the case of concave mirror, so rays which are coming from a very far away point will be parallel to the principal axis. So such rays after reflection converge to the focal point. So concave mirror has a real focal point such that parallel rays incident converge to the real focal point. Whereas when we talk about convex mirror, the center of curvature is behind the pole. So the focal point is also behind the pole. So rays which are parallel to the principal axis, they diverge in such a way that they appear to be coming from this virtual focal point. Okay. So F is equal to R by 2 implies that the distance PF is half of the distance PC here. Again here F is equal to R by 2 implies that the distance but here F will be a negative quantity with our sign convention. Here F will be a positive quantity with our sign convention. Okay, so with this now, we'll understand the concept of extended objects and magnification. So whether we are dealing with convex or concave, the method will be the same. So let's say this is the center of curvature and this is the focal point. Now we consider an extended object like this. Now let's here, for example, consider an object EB like this. Then to understand where its image is, we can of course use the UV formula, but we can also understand from a ray diagram that any ray parallel to the principal axis after reflection will pass through the focal point. So that's how this ray goes. And we can also understand that any ray, for example, incident at the pole, so such a ray after deviation goes something like this, such that angle of incidence is equal to angle of reflection. Just a moment, I'll reshare that. So here, this ray, this second one that we've drawn, this will be such that this angle is equal to this angle. This angle of incidence here will be equal to this angle of reflection here. And so we will see that the image of the point B is now formed here, because these two rays. So this becomes the real inverted, and in this case diminished, image of the extended object AB. So incident ray parallel to the principal axis, it goes through focal point after reflection. Okay. And incident ray at the pole. So using that, now we can see that A prime B prime is the real inverted, and in this case diminished, image of the object AB. So now we can also see that triangle EBP and triangle A prime B prime P are similar right angle triangles. So because I is equal to R. So this is a magnification formula with sign convention such that magnification is positive means it is upright, and magnification is negative means that it is inverted. So in the case of mirror, you will see that inverted means that it is real, upright means that it is virtual. Okay. And magnitude of M is greater than 1 means that it is magnified, and magnitude of M is less than 1 means that it is diminished. So for example, in those questions we had done a while back, suppose our U was, like minus 180 and our V had come out to be minus 36. So our magnification, which is minus V by U, becomes minus of 36 by 180. So this is minus of, so minus of 0.3. Sorry. Minus of 0.5. Minus. So it is a real inverted and diminished image. But for example, if we have another situation where U was minus 45 and our V came out to be minus 90. Because R was minus 60. Here also in this example, R was minus 60. Then our magnification here comes out to be minus 2. So this is an example of real inverted magnified image. But another example we had was U was minus 15 and V was plus 30. So here our magnification would come out to be plus 2. This was an example of upright, virtual, and magnified image. No, the formula for magnification is minus V by U beta. So if U and V are of same sign, then it comes with minus sign. not with plus sign. Yes, yes. No, so the formula with sign convention is like this, is minus v by u. Here it's not mod of v and u, it's minus v by u where we substitute with sign. Whereas mod of m is, yeah, that mod of m is telling you whether the size is greater or smaller, but the algebraic sign being plus or negative tells you whether it is upright or inverted. So always real is inverted and virtual is upright. That is the idea. Yes, understood this now? So that is all about spherical mirrors. Okay. Now we move on to refraction. So refraction is basically, as you know, it is about the bending of light.
So can you show the last part for like a second?
Yes. Okay.
Yes, sir. Done. Thank you.
Sir, can you please minimize a little?
Okay, people. So now coming to refraction. So as you know, as a phenomena, refraction is the bending of light as it passes from one transparent medium to another. So we have the definition of refractive index. Which we'll denote with the symbol mu. So refractive index of a medium is basically equal to what? It is C by V. So again, you can think of it like an experimentally measured quantity, which is dimensionless. Where C is speed of light in vacuum. Which is approximately 3 into 10 raised per 8 meters per second. And this is speed of light in the given medium. So as you know that speed of light in any material medium will be less than speed of light in vacuum. So mu for any medium is greater than 1. So this is one thing about refractive index. Okay. So this is, you can say, the definition of absolute refractive index. We also define refractive index of a medium relative to another. So if we have so these are absolute refractive indices of mediums A and B. Then we define refractive index of B with respect to A. Like this. Okay. So the notation should be clear for relative refractive index. Okay. So next we understand Snell's law.
Sir, just a minute. I wanted to note down.
Okay.
Done, sir.
Okay. Yeah. So last line is that refractive index of medium B with respect to medium A. Okay. refractive index of a certain medium B with respect to medium A, it is defined by VA by VB, where VA is the speed of light in medium A, VB is the speed of light in medium B. So you can see the relationship between these also. No? Absolute is with respect to vacuum, so it's C by V. But relative to each other, mu of B with respect to A is mu B divided by mu A, which becomes VA by VB. So if you just apply these formulae, you can see how that works. So the only important thing here is to understand the notation. When we write mu of B with respect to A, B is the subscript on the right and A is the subscript on the left. Okay. So that's just a matter of notation. Now we come to the main experimental law for refraction. Just like we have the laws of reflection, like that we have Snell's law, which is the law for refraction. It tells us how light bends as it refracts from one medium to another. So let's say this is the boundary line between two refractive media. Okay. So this is medium 1, let's say, of refractive index mu1. That means it's the absolute refractive index. Okay. And this is medium 2, which is of absolute refractive index mu2. Okay. So then if we have light incident from one medium to another, then once again, at the point of incidence, if we draw a normal to the surface bounding the two media, the angle made by the incident ray, let's call this in this case, we'll call it theta2 because it is in medium 2. Okay. Now it will tend to bend depending on the refractive indices. Okay. So I'm assuming now it's going to bend like this because I'm assuming that medium 1 is denser than medium 2. So the refracted ray in this case bends in such a way that it makes an angle theta1 with respect to this with respect to the normal at the point of incidence. So this is a case where mu1 is greater than mu2. So we basically say that medium 1 is denser than medium 2. So Snell's law tells us that mu1 sine theta1 is equal to mu2 sine theta2. Okay. So the important thing is here, it can be reversibility also. So in the case shown above, theta2 is the angle of incidence and theta1 is the angle of refraction. Okay. And the ray is transmitted from rarer to denser medium because mu1 is greater than mu2. It is from medium to medium 1. So that ray bends towards the normal. Okay. But in the same pair, for example, if we had a situation like this now, so same thing, mu1 is greater than mu2. But now this is the incident ray. So this will bend away from the normal. So here, So this is all stuff that you're familiar with. You know this very well. But just make a note of this anyhow. So this statement is called Snell's law. And of course, part of Snell's law is also that incident ray, refracted ray, and normal are coplanar. So this second statement is also part of Snell's law. Okay, we will. So this is Snell's law. So we will quickly look at the main important application of Snell's law for refraction at plane surface. Okay. For what is called normal view. I'll explain what we mean by normal view. So we'll understand this with a somewhat simplified example today. We'll look at more applications in the next lecture. So let's say this is water, which is of refractive index mu, and there's air outside. And there is a point object here, which is at an actual depth from this point of h. Okay. The distance OP is the real depth. Let's also say that there is an observer who is viewing this from above. So that's what we mean by normal view. Observer, he's having the normal view. That means he lies along the normal. Okay. Now, of course, there will be one ray which goes exactly along the normal and it is undeviated. But one ray is not enough to produce an image. So we need to imagine a second ray which is very close to this one. So if we consider a second ray, so it's very close to this one. So while it's little challenging to draw in the diagram, you can understand it conceptually. So again, it's that case of nearly paraxial ray kind of thing. So let's consider a ray like this. Now what will happen is that this will bend slightly away from the normal. This. So if I draw a very magnified diagram of this, if I magnify this a lot, you'll see that this is your refracting surface. This is your normal. Somewhat like this. So this is the angle of incidence. You can see this is the angle of refraction. Okay. So by Snell's law, mu sin I is equal to sin R, because refractive index of air is 1 and refractive index of water is mu. Now since we are taking paraxial rays only, because it is a normal incidence, we have I is a small angle. So R is also a small angle. So sin I becomes approximately I or tan I, and sin R becomes approximately R or tan R. So when we look at this magnified diagram, this incident ray was coming from the actual object. And the refracted ray, when you produce it back, it appears to be coming from some point like this. Okay. So in this diagram, this point will appear to be somewhere here. Okay. Or we can even call it O prime, which is like the not the actual object, but where it appears to be. So the object appears to be at the point O prime, whereas actually it is at the point O with respect to this pole. So you can see that in this diagram, this angle here is again R, and this angle again is I. So if this distance is X, you can see that from this, sin I by sin R, which is approximately tan I by tan R, becomes equal to 1 by mu. Okay. So tan I, you can see, is the real depth. It is like this distance X divided by the real depth OP, whereas tan R is the same X but divided by the apparent depth. So 1 by mu. Okay. So we can see from this that O prime P is OP divided by mu. So the apparent depth is the real depth divided by the refractive index of water in this case. Okay. So objects appear to be nearer from the water surface than the true depth. So this is an important formula, okay, and its application. So make a note of this, and with this we complete today's session. Okay, you will find the same derivation in HC Verma also. So I will send a list of questions that you can do from HC Verma in this week from geometrical optics, and get familiar and comfortable with spherical mirrors and refraction at plane surface. And then next week we will continue with refraction at planes at spherical surface, and then thin lenses. Yes, so basically replace water with any other liquid or glass or something like that, any denser medium, the same formula, but mu is the refractive index of that one. Okay. Similarly, later we'll see that the medium outside also, instead of air, it can be something else. So for example, you are underwater and there's some glass below the water, and you're watching an object which is on the other side of the glass. So similar kind of concept will be used, but this formula has to be tweaked a little for that. Okay. So we start with the basic application, that is you're watching from air outside, but normal vision. So the real depth of the object is suppose X, then the apparent depth becomes, the apparent depth is that O prime P. The object appears to be at the point O prime, and that apparent depth becomes real depth divided by mu. So it's less than. Okay. So with that, we complete today's session, people. Thanks for attending, and wish you a very happy Diwali in advance, and have a nice day, people.
Bye, sir. Thank you, sir.
Sir, thank you.
Thank you, sir.
Thank you, sir. Bye.
Thank you, sir.